right, so let's kind of talk about a chemical reaction involving the halogenation of a hydrocarbon, and we can talk about the halogenation of methane. So halogenation of methane, hopefully you can read my handwriting. And we can start off with methane. And we want to combine that with chlorine. And it would be dichloride, basically. And you have to add something. And anytime you see HV, this means it's a photon. And so this is photocatalytic. This would be a photocatalytic reaction. And what we end up with now, I should probably write this somewhere else. And let me just do it kind of down here. Sorry. People are groaning. And then you have to do something. You'll have a remaining chlorine. Oh, okay. Whew. Thought I was blocking it out. And you'll have a remaining hydrogen left over from this chemical reaction. And so you'll get, oopsie, how embarrassing. You'll get hydrochloric acid. All right, so we're taking methane, combining it with some chlorine gas. We're combining two gases, and that's horribly written. I'm sorry. Hopefully that's better. And then chlorine gas. Photocatalytic process, so we'll get, I believe this is chloromethane. And hydrochloric acid. So chloromethane is a halide. If I didn't mention that hydrogen containing, no, I guess I didn't. So halogen containing organic compounds are halides. And kind of other examples of halides. So halide has kind of a simple structure of, it can be this, where X is the halogen, R is generally the hydrocarbon. And let's see if this follows my rule. Kind of. Okay, so halobenzene kind of follows what I'm doing here. Other halides are like refrigerants. And so an example refrigerant halide would be kind of a mixture of fluorine and chlorine. This would be in gaseous form. Another common halide is so this would be kind of a polyolefin halide, which is very, very common. We use it fairly often. Would be this, and Teflon. And I need to draw either a squiggly, excuse me, there you go, or parentheses. So Teflon. Kind of talk a little bit about safety concerns. You don't ever want to burn, excuse me. So this is entertaining. You don't ever want to burn things like PVC or Teflon. And let me try, sewage. That was another conversation. We'll bring that up again. I edited it out and I thought I erased it. Excuse me. You don't want to burn halide containing or halogen containing polymers. Kind of a safety thing. Kind of a note of safety on halides is we'll kind of make it big. We don't kind of writing it out and taking the time to write it out. Don't ever burn halogen containing plastics. Fluorine, bad. It's a toxic gas. In fact, there's been a lot of maybe not now, but when I was younger, there was a lot of press because Teflon's used on nonstick cookware. And a gentleman I remember very distinctly was cooking in his kitchen. I don't know if he had a small place or what. His bird, he had a canary or some sort of bird in a cage next to where he was cooking. The bird died. And so that kind of set off kind of a health scare pertaining to people being nervous about fluorine cookware. And it's dangerous. You don't want to breathe in fluorine gas. I'm seeing a lot of fluorine-containing thermoplastics for 3D printing. That scares me if someone buys that for their house or something and starts trying to print these fluorine-containing thermoplastics. And when we get into 3D printing and additive manufacturing for polymers is one of the topics that we'll talk about in this class. I'll talk a lot about the safety issues associated with it because I think there's some dangers to the widespread use, and part of that is what's in it. Not all thermoplastics have halogens in them, but there are bad things in a lot of other thermoplastics that you definitely don't want to breathe. And it's not just elemental gases, if you will. It's also particles and stuff like that. PVC, you also don't ever want to burn, and also because you're giving off chlorine. Oops, I spelled burn wrong. Excuse me. So PVC don't burn, so chlorine, okay, was like the first chemical weapon, actually. Well, there's probably something else in antiquity, but first gas weapon. And the so-called mustard gas, I believe, and I should have Googled this before I make this claim, but chlorine gas actually is yellow. And I remember I was taking care of a swimming pool one summer, and the owner of the pool had the chlorine tablets stored outside, and moisture had actually kind of gotten in, and the pellets kind of started dissolving. And I remember, man, I opened it was like a 5-gallon bucket of chlorine tablets, and I mean this yellow cloud literally, and I'm not making this up, came up. I was coughing, and mustard gas might actually be something else, but it was really the first gas chemical weapon, chlorine gas, used in World War I. I think phosgene kind of comes in my brain as well. Let's kind of take a look back right quick. and because we're going to wrap up kind of this basic organic chemistry, this and the supplemental videos, and kind of see what else we want to kind of talk about. And okay, oh, we started off with hybridization. We'll talk a little bit more about hybridization right now because I think I kind of sold it short. Maybe we'll talk about that again. All right. Alkane, alkyne, ether. I had missed this because I went straight on to epoxy. Ether, another kind of ether, looks like this. I'm drawing it really poorly. Excuse me. Kind of on this, kind of fill in the gaps, and we're going to start moving on into the nitty-gritty of polymers, but if there's other organic stuff, we'll kind of come back to it. I kind of had forgotten to put this in here. I'm drawing it wrong again. I'm sorry. Should edit it. Maybe I will. This is an epoxide. And so this is also found in epoxy resins. So an epoxide is another one. Kind of, I noticed this on the subject of where were we? Kind of hybridization. I don't think I talked about this. This is sp3 hybridization, and so we'll kind of take a quick step back before I go too far away from this. So I didn't talk much about it. I said we would talk about it more again, and we'll talk about it even again when we talk about polymerization. But let's talk a little bit more about orbital hybridization. And and thiols. I forgot about this. Thiols. I'm very random today. I apologize. So thiols, they're smelly. Sulfur containing smelly. Probably should have made it yellow. Rotten eggs are in thiols, and I'll get back to the hybridization right now. But a thiol, they're smelly, rotten eggs. It's added to natural gas. So think about it, thiols, sulfur is kind of smelly. If you have sulfur with aromatics, you're in for a treat. Again, my little PSA, don't burn halogen-containing plastics. We're going to jump to another topic here. All right, we're going to talk a little bit more about orbitals, and then we'll kind of start jumping into polymer structure and polymerization. I think we'll also talk a little bit more about some topics that I didn't get. So I'm kind of filling in the blanks with this part of the lecture. And again, if there's something organic that we missed, we'll kind of cover it. And then some stuff is also in the supplemental videos, and so hopefully we'll get that. So more on orbitals. If we take a look at orbitals, the things we're mostly concerned about, particularly with hydrocarbons and plastics and that kind of thing, are s orbitals, and then p orbitals. And if you remember from other classes you've taken from me, or maybe you've taken from someone else, the S and the P, they actually have names. So S is sharp, P is principal, I hope it's this principal, not principal of a school like your pal. What is it? D is diffuse, and F is fundamental. And so SPDF are kind of the orbitals we care about. The ones we care about the most are s orbitals and p orbitals, and they have distinct shapes. So the s orbital is this kind of circular orbital, and the p orbital is kind of this lobule, kind of globular lobule. So circular and kind of lobular. So if we're not talking about an organic compound, but the one that is kind of used in a lot of textbooks actually is beryllium. So I believe this is beryllium hydride, BeH2. And so beryllium, if we look here, it's 1s2, 2s2. So your orbital, your 2s orbital is totally filled. All right, and so let me draw this a little clearer. Totally filled. Okay, so when the hydrogen comes along, what's happening is one of these kind of goes up to the 2p, but not really. This valence shell is totally filled, so for this beryllium to bond with this hydrogen, which only has one electron for each atom, something like this has to happen. But what really happens is not this. So you get hybridization is what happens. And in this case, for BeH2, it's straight up a 2p hybridization. So 2p hybridization is what happens. And so what you get is, I'm totally wrong. You get sp hybridization, excuse me. Made a boo-boo. sp hybridization occurs, okay? And so at the very beginning of the talking about this, let's see if I can do this. Come on. We talked about this sp3 hybridized state. In this sp3 hybridized state, it's going to have a different geometry, basically. And so it's kind of what I'm getting to right now is geometry. Doesn't look like I've written all that much. Oh, and I was doing this like shrunk screen, but that's all right. All right, so you have sp hybridization. Okay, and sp hybridization, your lobes kind of start looking like this. So here's a p orbital, here's an s orbital. So let me just redraw it. Again, it's a circle. This p orbital is lobular. And it's actually supposed to be pretty much the same on either side. And an sp orbital looks like this. So it's kind of a mixture of them both. And let me draw that a little better. sp orbital. So it's kind of a mixture of both. So if we go back and look at our beryllium hydride, instead of having two s orbital electrons, we have two sp orbital electrons. And so their orbitals, oopsie, the orbitals are going to kind of overlap. And let's see if I can draw it well. I'm just going to draw it like this for lack of a better. And the orbitals kind of repel each other. So now we have one electron in these sp orbitals, and then the hydrogen comes in. And so we'll just kind of color code it. And I shouldn't be using red and blue to color code. But now we have the hydrogen with its s orbital electron, and then we have the beryllium with its sp hybridized orbitals. And what happens here now is these orbitals are trying to be as far apart as they can from each other because the two sp orbitals from the beryllium repel one another. And so the equilibrium point for this molecule ends up being 180 degrees. All right, so that's an sp hybridization. All right, so since we made two sp orbitals, so sp hybridization is two sp orbitals. And let me highlight that. Oh, come on. There we go. Thank you, undo. So sp hybridization, two sp orbitals. You get this 180 degree configuration. All right. So we talked about sp hybridization. And now we want to talk about sp2. And so drew the 2 in the wrong place. I think it doesn't matter that much. But anyway, sp2 hybridization. So if sp hybridization has two sp orbitals, sp2 3 sp orbitals. So 3 sp orbitals. And the example that is oftentimes given is that of borane. It has different chemical names too, but let's just do. So boron and 3 hydrogens. The electronic configuration of boron has a p orbital. And so boron is helium 2s2 2p1. All right, so we have 1 p electron. And then we have 2 s electrons. And so 1 p let me write this a little better. I apologize. So 1 p and then 2 s electrons. All right. So this means that this one's going to go down in an energy level and become a 2p orbital. Sorry, an sp orbital. It's embarrassing I make that error. And so they're going to go down in energy, and these two are going to go up in energy. And they're going to make 2 sp orbitals. And so now, instead of having this electron configuration, it's basically going to be, excuse me, it's going to be sp. And I'll do it again, kind of like I did above. Oh, come on, excuse me. Just undo it, make it a smaller pen. And the hydrogen now, make it green. The hydrogen now is going to help fill this shell, basically, if we want to think of it again in terms of Hund's rule. So that's sp2 hybridization. One thing about sp2 hybridization now is if I draw it, they're equally distributed at 120 degrees. So this is sp2 hybridization. And I kind of drew the nomenclature a little wrong. sp3 hybridization. we talked about with methane. And we talked about it way at the beginning of when we talked about this jazz, if you will. Oh, come on now. Excuse me, I'm sorry. I should have just redrawn it instead of fiddling around. So what do we have? You may have guessed we have 4 hybridized orbitals. Okay, just kind of by the convention is going. And so let me go back down to where we're talking about it again. I'm kind of thinking the recording software slows things down because I practice going back and forth, and it's much faster. sp3 hybridization. There's 4 sp orbitals, hybridized orbitals, if you will, and they have their own kind of geometry, and I'm going to kind of try to draw it as best I can. We kind of have this orbital. And I may have a supplemental video on this. These are supposed to be my lobes. And the kind of the trick almost looks like a happy face. The key angle, and you may have seen this elsewhere, is this 109.5 degree angle. And a lot of times the bond angles, okay, if you have the bond angle specified, you can be told or you can infer what kind of hybridization occurred to make the molecule. And if you look at some of these molecules, you'll able to kind of get an idea. And it's roughly, so this 120, sometimes there's some deviations from the 120, but not that much. It's pretty close. And people that do a lot of experimentation on this, I guess, know a little bit more than that. But sp3 hybridization, 4 sp3 orbitals, it's the one we kind of talked about at the very beginning. And all right, so let me kind of end this, I guess, kind of overview of basic organic chemistry with kind of a recap of some of the stuff we already talked about, but throwing in a little bit more information. And so if you remember, we had alkanes, and get my pen to work. Always embarrassing. Oh, what else did I undo? Oh, well. Alkanes. And remember, they had a single carbon bond. So single carbon. And a couple of things I didn't really talk about. If you have butane, and I didn't talk about isomers. Isomers are kind of a big deal. So you have butane, and here's one way you can draw butane. And so 1, 2, 3, 4. So this would be 4 carbons. So this would be butane. And so this is a chain structure. But you could also draw butane another way, and you could draw it this way, almost like a peace sign. So this is an isomer, butane and isobutane. And so an isomer is basically the same chemical formula. However, you have multiple chemical structures. And so just for memory's sake, there's a carbon at every kind of point there. And here there's a carbon, 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 carbon at the middle. Okay, so it's still C4H10. And you can kind of add the hydrogens, if you will, to kind of figure it out, how many hydrogens there are. And let me kind of think about it a little bit. Probably there's 2 here, and 3 on the end for hydrogen. I'll go ahead and this is ugly. I know, I'm sorry. All right, so this is what butane would look like, and then isobutane, a little bit different. Let me think about isobutane. Probably 3, 3, 3, and 1 here. All right, so 2 flavors, C4H10. Single bond carbon still, so this is still an alkane. It's a butane. Something else, kind of talk about carbon numbering. So you see here we have a chain structure and we kind of have the P sign structure. But if you have kind of, this kind of chain structure in an organic molecule, let me kind of draw this. And then I didn't draw this, so this is kind of similar. And I do not envy anyone who majored in chemistry. If you have this chain structure, and you see we kind of have 2 chains, and so we have a chain that goes this way, and then we have a chain that kind of goes this way. And so you want to number the chain by the long way. So numbering and so you want to number the longest chain. All right, so number the longest chain. Sorry, my handwriting is bad. For something like this, you would want to number it going this way. So 1, in fact, let me use a different color to kind of make it a little more clear, hopefully. So 1, 2, 3, 4, 5, 6, 7. So number top to bottom. So number the carbons. So you want to number those carbons from top to bottom. You want to number the longest chain. We have isomers, so same formula, something that looks a little different. If your chain is longer this way, okay, so if I have this kind of, the longer chain is the parent chain, by the way. So if we have our, how many do I want to put today? If your chain is going this way, so if your parent chain is going this way, you number from left to right. All right, so here our parent chain was longer in the vertical direction, so we numbered from top to bottom. Here we have a different animal, or we have a different drawing of the structure, and so we want to number this way. All right, so 7 carbons. If we add a group now, we could add it to any one of these points, but we can only add it on the inflection points. We don't want to add it to the end, basically. So, because if you add it to the end, it just makes the chain longer. And so here, we want to add we can add a butyl group. And so this is 4, this would be for something or other. All right. So this would be like 4-butyl heptane, I think. Because hept is 7. We can add some other branches to this, and again, you can only add them to the inflection points. You can't add them to the ends. And I'm almost saying that thinking I'm saying something slightly incorrect, but if we want to add a methyl group, so heptane is our parent chain. We're adding stuff to heptane. So here at the 4 carbon, we've added a butyl group. So 4-butyl heptane. We can add a methyl group here. I'll do it in a different color. So we added a methyl group to the 3 carbon, and so we could call it and I'm really bad with my capitalization. The B and the H didn't need to be capitalized, actually. I'm sorry. So 4-butyl, that says butyl methyl heptane. We could add other methyl groups. And so I can add one here to 2. We can just kind of recolor the 3, and we can add this one to the 5. And so now we have 3 methyl groups. And so we want to do the name now. So 4-butyl, and I believe the naming convention, the bigger molecule comes first, and it ends with the parent chain. So 4-butyl, we have a methyl group at the 2, the 3, and the 5 carbon. So 2, 3, 5, we have 3 methyls, so it's trimethyl. So 4-butyl 2,3,5 trimethyl heptanes. That's a mighty big alkane. So it's an alkane structure. Let me think of something else to it. I think we've covered kind of all the rules I think are important, perhaps, for alkanes. And there's many more. I mean, there's whole classes. Oh, one more thing. So I talked about ring structures. So ring structures. So in the supplementary video, the gentleman talked about, different cyclic structures as well. And so the only ring structure I've really talked about on this kind of hand-drawn stuff has been benzene rings, and we'll see that again. But there are other cyclic structures that are not benzene rings or arenes, and they find their way into they find their way into polymers as well. So there's more ring structures than arenes in the polymer world. And so ring structures, so we're still talking about alkanes or recapping alkanes. So cycloalkanes, this one, it kind of looks like a triangle. So this is cyclopropane, cyclobutane would be more of a square. And so what do we say butane was? We said butane. I have to go back and look. I'm sorry. I'm embarrassing myself. C4H10. So we have, let's see if I can do that. We have a carbon at each inflection point of this square. And let me kind of draw it a little better for you. In fact, I do this on grid paper or grid so I can draw better. And then I don't use the grid, so yay. Painful to watch, I know. All right, so close to a square. So there's a carbon on each end. I have to think about how many hydrogen would be on each end, but anyway, so cyclobutane, cyclopentane, it's like the pentagon. Yeah, this is a little messy. Cyclohexane, it's a hexagon, and I'm going to butcher the heck out of it, sorry. So cyclohexane, cycloheptane and cyclooctane, I won't draw them, but heptane, of course, is a 7-sided polygon, and octane is like a stop sign, so an 8-sided polygon. Something else is we talked about cis and trans in, or the gentleman did in the supplementary video, and I think we'll just leave it at that. Cis is on the same side. I'm sorry, cis is on the same side. Trans would be on the other side. So let me just draw it just because I brought it up. And so if we have this kind of pentane structure, and we have an ethane, and so if you remember the solid kind of arrow triangle-y thing means it's coming out of the board or out of the screen. So and the kind of dashy one means it's going into the screen. So, and then out. And that's kind of bad, sorry. And so this is kind of a different way of showing cis and trans. This is more of a three-dimensional way rather than saying everything on the same side, like top and bottom. So this one would be cis. And we'll probably see this again. And other things, there's different conformations that we kind of want to talk about. And you see it a lot with nanotubes and the way nanotubes are arranged. But if we take cyclohexane, so if we take cyclohexane, this can make another structure. And I'll talk about the nanotubes in a little bit, or I have a paper actually I can give you that you should check out. So we have 1, 2, 3, 4, 5, 6. So again, we have 6 carbons, and there's single bonds between the carbons, so there's still a cycloalkane. And but this is a different conformation of the same molecule. So this is a so-called chair conformation. And nanotubes, the way nanotubes are arranged is similar to this. There's different conformations for nanotubes. And pretty much organic chemistry. What else do I want to kind of throw out? And you've seen some stuff with the supplemental videos, and I don't want to scribble something that doesn't look quite as nice as a well-produced video. But let's talk about alkenes one more time, just a little bit to kind of close it out. And then we'll kind of move on to polymers, talking about polymers. And I'm a little slow because I'm kind of thinking about it as I do this, even though I did kind of think about it before I did it. So excuse me. Okay, so alkenes. And actually, this is kind of important because it's a direct segue into what we're talking about, olefins. So we already said it before, but this is AKA. So it's AKA olefins. And AKA olefins, so alkanes play a very big role in polymers. And we're going to kind of jump into a lot of stuff involving alkanes in the next kind of sections. And they lead to a lot of different things, and I kind of like this figure that I kind of should just reproduce, but I'll just draw it out. And alkenes, if they're drawn, you want to draw them this way, and then this angle looks kind of familiar. Perhaps it's a 120 degrees, perhaps. And we know what kind of hybridization caused that, I believe. So alkenes lead to a lot of different things. So we have the basic alkene structure. So this is the basic alkene structure, and then we have the sigma bond, and we have the pi bond. During polymerization, this pi bond is going to break, so we can bond one monomer to another. But alkenes themselves, just in the subject of organic chemistry, not really talking about polymers directly, leads to other things. Okay, so we have another structure related to alkenes, alkene derivatives perhaps, and you have a hydroxide and chlorine. So this is called a halidrin. Alkenes can lead to alkanes if you break the bond. So we have a single, So it leads to alkanes. And we've seen this before, where it can lead to a carboxylic acid. Oops, why are you doing that? We've seen this. This is another ester, right? So we did this. I'm drawing it slightly different than I drew it above. This is an epoxide. Finds itself in epoxies. Alcohols. Which very similar. With the exception, instead of a hydrogen, you have a chlorine for the halogen. So alcohols have similar chemistry. We talked about this, halides, which is similar to this minus the OH. Halide. And we said that the X meant halogen. And so Teflon was an example, PVC, another example. and we talked about it pretty extensively above. And one more, or two more, sorry. Very similar to the epoxide without the oxygen. This would be a cyclopropane. So a ring structure coming from an alkene that's not an arene. And one more. And so this is an aldehyde. And so like formaldehyde. And we talked about the supplemental video talked about saturation and actually used fat as an example, which is kind of interesting. I think I'm going to, well, let's talk about ring structure, one more ring structure. And so if we have now, so we'll just kind of do chains and rings. This is alkenes. And so double bond. And so this is pentene. But the double bond is for the first carbon, between the first carbon and the second carbon. And so this would be called 1-pentene. So it's an alkene because we have a double bond. If we have an isomer of this, and we have our double bond here, the double bond is between the 2 and the 3, so it starts at the 2, so it's 2-pentene. The numbering follows, and I should have said this first, the numbering follows the same rules that we had before. So if it's horizontal, it's left to right. If it's vertical, the longest chain's vertical, it's right to left. So 1, 2, 3, 4, 5. Pentene can also form a ring structure. Oops. We wanted to just try to homogenize our colors. And so we already know about cyclopentane. But if we have a double bond on one of these, it's cyclopentene. And I talk about rings simply because there's a flavor of polymerization called ring opening polymerization. And so if you open this ring, you leave it free to bond with another opened ring molecule. And another thing to talk about is the numbering of a ring structure like this. And so you want to number it so the double bond is on the lowest number of carbon. So this was 1-pentene, and so this is cyclopentene. And so this double bond is between this carbon and this carbon. So you want to start your numbering here. So 1, 2, 3, 4, 5. Okay, that's kind of the rule, and the rules are good because they kind of help keep some of these things straight. And we'll talk a lot more about alkenes, and we'll start calling them olefins. Just to kind of end it on something that we've already kind of talked about. If you have an alkene and we'll try it black, sorry. If you have an alkene, we have a double bond, and I made that one a little big. Oh, my mistake. Oh, well, it was just the computer's thinking about it. All right, so if we have this, and both of these hydrocarbons are on the same side. So this is cis, and I'm probably overcomplicating this when I do this. I could have just drawn R. So let me just do that. So our hydrocarbons are on the same side, and then here this is trans. So we're drawing this in a planar way. We're not having something coming in or out of the board or screen as we had up here. Oops. Here, cis and trans. So kind of two different ways to look at cis and trans. And I'm going to end kind of doing our basic organic chemistry here. And if more organic chemistry topics come up while we're doing polymer stuff, we'll stop and touch base with that again. And hopefully this has been informative to you guys. Thank you.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.